Okay, I wanted to finish up section 4.3 here in this video. We're looking at how derivatives affect a graph, and so far in the section we've talked about the first derivative test and then the concavity test. Of course, if there's a first derivative test, there's got to be a second derivative test, right? And so, okay, here's the second derivative test. It says, let f double prime be continuous near C, and f prime of C equals 0. Okay, so C is a critical number. Item 1, if f double prime of C is positive, f has a local min at C. If f double prime of C is less than 0, f has a local max at C. And if f double prime of C equals 0, or if f double prime of C does not exist, the test fails. And basically what I mean by that is the test won't tell you if you have a local max or a min. You'll have to use the first derivative test to be able to get that information. Okay, a couple things. So first of all, don't get the second derivative test confused with anything with concavity. Okay, in the concavity test, we were using the second derivative, but that was a totally different test though. Okay, that is just telling us where the function is concave up or concave down. Okay, the second derivative test tells us nothing about where we're concave up or concave down. It tells us where we have mins and maxes, potentially. Okay, just like the first derivative test told us where we have local mins and maxes. All right. Students sometimes get those confused because they think second derivative, you're automatically doing things with concavity. Don't do that, okay? Let's take a look at an example here. So in this example, I want us to find the local extrema for the function f of x equal 5x cubed minus 3x to the fifth. We'll use the second derivative test to do this problem. Well, f prime would be 15x squared minus 15x to the fourth. 15x squared is in common to these two terms, so I can factor that out, and the leftover would be 1 minus x squared. And then I can set the factors equal to 0. 15x squared equals 0 means that x is 0. 1 minus x squared equals 0. Add x squared to both sides and then take the square root of both sides. Don't forget about the plus or minus when you do that, so x would be plus or minus 1. Okay, now these would be my critical values. So in the second derivative test, I'm supposed to plug those numbers into f double prime. Well, f double prime, I can just use the power rule on these two terms here. It's going to be 30x minus 60x cubed. Okay, let's go. So in the second derivative test, there is no chart. Okay, I was making charts in the first derivative test. The nice thing about this test is that there is no chart, but of course I still need the second derivative though. So let me plug these three critical values into f double prime. If we plug in -1 into f double prime, we get -30 plus 60 is 30. 30 is a positive, and so that will imply that I have a local min at x equal -1. Okay, if x is -1 and you plug that into the function, you'll have -5 plus 3 is -2. Let me plug 1 into f double prime now. 30 minus 60 is -30. That's a negative, so that means that we have a local max at x equal 1. Okay, and when x is 1, we plug that into the function. 5 minus 3 is 2. Be careful about this. I will have students get the wrong conclusion because they think we have a positive output, so we have a local max. Negative means local min. Be careful about that. It's switched here. Okay, if you have a positive output from f double prime, you have a local min at that spot. A negative output from the second derivative means that you have a local max. If I plug 0 into f double prime, I get 0. Okay, so the test failed for when x is 0. I'd still like to know if I have a local min or a max at 0, 0, so I'd want to use the first derivative test as my next option here. Okay, now the first derivative test is where we are producing a table. Okay, so I've got that set up here. Interval, number chosen, value of f prime, and then our conclusion. And I've got 0 positioned on the number line. Now, here's the thing. I already know what's happening at x equal 1 and x equal negative 1. So I don't want arrows shooting off in different directions, covering the entire real number line. Okay, I'd like to know what's happening between 1 and negative 1 at x equals 0. So I'd want to indicate those values here on the number line above my table. Okay, and now I can select my test values. So negative 1/2 is one number in this first interval. If you plug negative 1/2 into f prime, negative 1/2 squared is 1/4 times 15 would be 15 over 4. Negative 1/2 squared is 1/4. 1 minus 1/4 is 3/4. 15/4 times 3/4 would be 45 over 16. That's a positive, so that means that we're increasing on that part of the graph. How about if I plug in 1/2? Well, the result is going to be the same since I'm squaring x, right? I'll get the same result as when it was a negative 1/2. 45 over 16 is the value of f prime when x is 1/2, and so I'm going to be increasing. Okay, I'm increasing and then increasing again. That means that this point 0, 0 is neither a local min or a max. Now, if I were to sketch the graph here of f of x, of course I got some key information that can help me do this here. I know that there's a local min at negative 1, negative 2, and there's a local max at 1, 2. Now 0, 0 is neither a local min or a max, but there's a reason why x equals 0 came up in the calculation. Like there's still something interesting happening at 0, 0. You'll notice that I got this squiggle going on at the origin. Okay, that's what's going to happen here because, like I said, there's going to be something interesting happening at 0, 0. Okay, if the curve was just kind of heading upward and passing right through the origin, that's not really anything interesting. Okay, there'd be no reason for that number to come up in the calculation. So that's all. And of course, I can see, you know, there's going to be a switch in concavity too. Now, I didn't do anything with the concavity test, but I could, you know, to have, you know, to figure out any of those inflection points if I wanted to. But so here'd be just a kind of a quick rough sketch of the graph of f of x. Let's take a look at another example. Okay, find the local extrema for the function f of x equal x squared times e to the x. And again, we'll use the second derivative test. So I would say, you know, in general, make sure that you know both tests. Okay, you will see both of them. But I would also say that the first derivative test is probably the more common test, just because, you see, the problem with the second derivative test is that the test can sometimes fail. You know, so it's like you should have done the first derivative test anyway, because that possibility can come up. Now, I would say that, you know, in the case of using the second derivative test, if you can, of course you need the second derivative, but if you can see the second derivative, and if that doesn't seem like so bad of a calculation, I would probably say use the second derivative test, you know, rather than creating a table. It'd probably make the problem quicker. Okay. Now, if calculating the second derivative test looks very brutal and time-consuming, like let's say you have a quotient rule, and inside the quotient rule you get a chain rule and a product rule and all this stuff, then no, that's not a great option, right? Because you know, there's one little slip up and there goes the whole, you know, calculation of the second derivative, and that, you know, it's kind of making the problem more difficult. Then I'd probably say just stick with the first derivative test. So, but anyway, let's use the second derivative test here. F prime is going to be a product rule. So the first is x squared times the derivative of the second derivative, e to the x is itself, e to the x, plus the second, e to the x times the derivative of the first, derivative of x squared is 2x. Simplify that. E to the x is in common to these two terms. You can factor that out, and that'll leave you with x squared plus 2x. Set this equal to 0, And okay, e to the x equals 0 has no solutions. Since x is in the power, there's no x value that's going to return 0. X squared minus 2x, x is in common to those two terms, so you could factor that out. And you'll have x times x plus 2 equals 0. That means that x is 0 or x is negative 2. So I'm going to have two critical numbers here, and I'll need to plug those into f double prime. F double prime would also be a product rule. And so let me use that. Okay, the first is e to the x times the derivative of the second. Derivative of x squared plus 2x would be 2x plus 2. Plus the second is x squared plus 2x times the derivative of the first. That's e to the x. Okay, e to the x, again, is in common to these terms, so let me factor that out. The leftover then, you got x squared. Here's 2x plus 2x is 4x, and then plus 2. And now I got to plug these these two critical numbers into f double prime. So, okay, if I plug 0 into f double prime, I got e to the 0 is 1, and then times 2 is 2. 2 is a positive, so that means I'm going to have a local min at x equals 0. Okay, when x is 0, y would be 0, and I plug that into the function. So 0, 0 is going to be, I get a local min there. If we plug negative 2 into f double prime, we're going to have e to the negative second, and then times negative 2 squared is 4, minus 8 is negative 4, plus 2 is negative 2. E to the negative second, if you were to check that, that would be roughly 0.14, I believe, but it's positive, times a negative would be a negative. Okay, negative 2 e to the negative second would be the exact, but that's a negative number. Therefore, we're going to have a local max at x equal negative 2. If x is negative 2 and you plug that into the function, negative 2 squared is 4 times e to the negative second. Okay, 4e to the negative second, if you were to go to the calculator and type that in, I was getting roughly 0.54. And yeah, so that point there, that's going to be a local max on the graph. Here's a quick sketch of the graph. So, okay, I've plotted the min point at 0, 0, and here's the max point at negative 2.54. And so there's going to be a hill there. Now, it might be interesting to note that this graph will have a horizontal asymptote on it. Now, an algebra student is not going to be able to know that because this is not a rational function, okay? Only a calculus student would be able to see this because you'd have to work with limits. If x is heading outward towards the left, approaching negative infinity, then e to a negative power would be the same as 1 over e to the power that would be a positive. Something that we're going to see in the next section is that an exponential is going to grow faster than a power function. In general, that would be true. An exponential will always grow faster than a power function. So I could write this as like x squared divided by e to the negative x. And the denominator then would be growing faster than the numerator. Well, what that means is that the y values are going to be getting very minuscule. Right? They're going to be getting closer and closer to 0, so this curve would be approaching the x-axis, but it's never going to get there. Okay. Now, if x is positive, let's say x is heading out towards infinity, x squared would be growing without a bound, e to the x would be growing without a bound. You've got two things growing without a bound, and so the product would be something that is growing without a bound. Therefore, the curve is going to be heading upward and outward into quadrant 1. Here's one point that I had plotted, like if x is 1, you get e. Okay, so here's the point 1e on the graph. I have one more example in this section. There's a couple of problems like this one in the section. I like a problem like this because it's kind of a good summary of the things that we've talked about in the section, okay? So let's take a look at this. It says, use the given information to sketch the graph of f of x. I've got things about the function, things about the derivative, and things about the second derivative. I want to sketch a graph. Well, f of 0 equal negative 2 means that the point 0, negative 2 is on the graph. F of 1 equals 0 means that the point 1, 0 is on the graph. F of 2 equal 2 means the point 2, 2 is on the graph. Okay, now f prime of 0 equals 0. What does that mean? Well, it means that at x equals 0, I'm going to have a possible min or max, right, using the first derivative test. F prime of 2 equals 0 means that at x equal 2, I'm also going to have a possible min or max. Now, I say possible because, you know, in the first derivative test, you could have something where it's like increasing and then increasing again, and you're not actually producing a max or a min. So I wouldn't conclude that I've got a max or a min quite yet. But you see in the next line, the next two lines, f prime of x greater than 0 on the interval 0 to 2 means that we're increasing on that part of the graph. So if I'm between 0 and 2, the curve is going to be rising. Of course, anywhere I draw a tangent line, the tangent line would have a positive slope to it. F prime of x less than 0 on the interval negative infinity to 0 and 2 to infinity means that you're going to be decreasing on those two parts of the graph. Okay, so the curve is going to be falling if I'm to the left of 0. Also, it's going to be falling if I'm to the right of 2, if I scan the graph from left to right there. Well, if I switch from decreasing to increasing, that's going to produce a min at this point, 0, negative 2. If I switch from increasing to decreasing, that's going to produce a max at this point, 2, 2. Okay, the slope of the graph at those 2 points is 0. That should make total sense to us because if I'm on the top of the hill or at the bottom of the valley and I draw a tangent line, it's going to be a horizontal line. F double prime of 1 equals 0 means that 1 is going to produce an inflection point. Or this point here, 1, 0. Okay, let's, we've already got that point plotted, but f double prime of x greater than 0 on the interval negative infinity to 1 means that we're going to be concave up on that part of the graph. Okay, and then f double prime of x less than 0 on the interval 1 to infinity means I'll be concave down on that part of the graph. So I'm going to be switching concavity here at this point. I'm concave up if I'm to the left of 1, and then concave down if I'm to the right of 1. So, of course, if I'm concave up, I'm producing a min at this point. If I'm concave down, I'm producing a max at this point. Okay, so here be just a sketch, you know, kind of summarizing the information that is there on the left. I like a problem like this because to me, it's a good recap of the things that we've been talking about all along in this section. You know, what does it mean for f prime of x to be greater than 0? Well, that means you're increasing, right? What does it mean for f double prime of x to be less than 0? That means you're concave down. Okay, so the idea with a problem like this is that they want you to think of the test and what it means when you're using the test. Okay, and you can use those that information there then sketch a graph. All right, there was a lot of information in section 4.3. But it's all very useful information, I believe, when it comes to graphing. Okay, and we'll be doing some more of this when we get into section 4.5. We will also be using the tests for some things later in the chapter. You'll see that. So be sure to look at the homework problems for me. They're on page 300. Look at the odd number problems that are listed there.